And now here is another works of my colleagues and in University of Tokyo, and I will present on behalf of the authors. And okay, so let's start. And the topic is on the towards event-aware urban mobility prediction system. And in this talk, I'll briefly introduce a series of our works on human mobilities and geospatial time series modeling, especially against various event scenarios, such as extreme weather like typhoon and blizzard, and pandemic and traffic incidents. And as you know, that in Japan is a country with various natural disasters, and like earthquake and typhoon, as we have been witness more and more natural disasters and extreme weather events, so for the for the discussions on the urban and mobility resilience is getting more and attracting more and more attentions because of the impact of this topic, not only onto the machine learning's data science community, but also for a general public. It is related to the resilient city or the community. Resilient cities and the communities which are aligned with the United Nations Sustainable Development Goals. We would like to refer to some of our original publications that is published in the KDD and the III for technical details and discuss a problem of our solutions. Yeah, so all right, so let's start. And first, let me briefly introduce the research background. Here are some facts and the numbers. We know that today there are large and various mobility and mobile phones and the sensors, networks, and the cyber physical systems existing, and they have been developing very fast. And we can see the numbers, like the global market size for smart city is over $50 billion, which is constant growth and expected to reach $300 billion by 2030. And so an urban mobility prediction system supports both the data-driven decision-making and the next generations of mobility services. So the motivations of our work is there are various urban events like the extreme weathers and the pandemics and traffic assistance, and as there are various underlying patterns and routines in collective human mobilities, prediction systems can be trained to capture the overall tendencies and make predictions. However, when urban events happen, such as holidays like Christmas or New Year's Eve, as we can see from these figures, that here is in the Washington, and on the New Year's Eve, it has a very sharp peaks of the taxi demand. And on the Christmas Eve and on very extreme weathers, here is a storm, I think, yeah, and the taxi demand drops significantly, and so in these scenarios, the traffic the mobility behavior is derived from normal situation. So in the first example, we can tell that the citywide taxi demand shows a very sharp increase on the New Year's Eve, but shows a very low demand on Christmas Eve or during the Blizzard. Here, this plot is a time series graph, histogram, which is plotted by printing all the time series of city together in one graph. In the second example, we select several sensors node. In the second example on the below, we select several sensors node. We select several sensors nodes on the road network of a city and plot their corresponding time series, which is it is noteworthy that the event like the traffic congestions and the accidents affect the traffic speed. Here is the sensors for the traffic speed, and we can see that the traffic jam or the traffic accidents, the traffic speed at this road segments drops also significantly. Yeah, so such kind of irregularities, it is very difficult to be predicted, especially considering the occasional and also the sudden changes in such kind of traffic systems. So it is very challenging for regular prediction system to make an accurate prediction under such kind of non-stationary scenarios. So for the then we would like to formulate the event caused sudden changes like this, and the problem. Statically, it can be expressed as a non-stationarity, which means the statically properties of the time series are not constant over time. In machine learning, there is a term called the concept drift that describes the similar data that the joint probabilities of a pair of input X and output Y does not hold over time. Therefore, we formally define our problems as sequence-to-sequence relationship between each pairs of consecutive time series segments. From note that there is the graph G that represents that underlying the geospatial relationship among the size of m nodes within a city space. We call this graph a geograph, which denotes how strongly related between each pairs of the node. Here is a node of a grid region. Here is a node of the grid region or sensor or road. In the equation, X is the graph snapshot for citywide observations on a set of C variables of a time slot. The presence of concept drift in this geospatial time series focusing task makes it closer in the real world scenarios. At the same time, it brings in extra complexity in machine learning. Our target problems in general is a concept drift. Okay, so So after formulating the target problems, we present our solutions at the here. So after formulating the target problems, we present our simulations at the architectural level. Firstly, we introduce the backbone models for simultaneous spatial and temporal modeling. Here, we employ convolution recurrent network, abbreviated as a CRN, in which the basic graph convolution operation handles the spatial dependencies, and the recurrent structure handles the temporal dependencies in an autographic manner. Specifically, spatial diffusion convolution embedded gated recurrent unit is implemented, which functions as a basic unit for spatial temporal modeling. Then incorporating the convolution recurrent unit in an encoder and decoder framework empowers CRN to takes in sequence input and returns sequence as output. On top of this framework, we perform adaptive learning for concept drift, given either caused by the temporal covariate drift or the conditional probability mapping. Conditional probability drift, or both. For the first case, we propose or regard it similar to an anomalous detections task in the multivariate time series, motivated by lines of research in video anomaly detections in computer vision. We leverage memory augmented neural network to recognize anomalous input samples. Specifically, we project this encoded hidden state from CRN network, CRN encoder, and use it to query for the parameterized memory bank, which is trained store mobility, traffic, and traffic prototypes, so that if an anomaly input, the memory bank will know it's different from its existing patterns in reconstruction. Upon this, to tackle the second case of the drift, we would want the predictive model is not fixed to its parameter theta for every example. Therefore, we leverage the idea of meta-learning to encourage the models to generalize over different scenarios. Particularly, we use hyper network to take the memory reconstructed representation to generate sample-specific parameter theta. And so based on the described methods, we did a series of research studies to validate our ideas. In the first case, we further feed the theta back to the CRN encoder and decoder as the kernel parameters for the graph convolution operations. It is motivated in a line of the research in computer vision called dynamic filter network. The idea behind this technique is to put convolution filters conditioned on its inputs for dynamic kernel generation in adaptation to different inputs. In first case studies, we had the history blizzard journals that happens on January 24th to 25th in 2016 in the US. From the ground truth time series histogram, we can see that the citywide taxi demand in New York City dropped to 0 because of the winter storm. While the state-of-art predictive model can only make native predictions by repeating the latest observation during the blade-art. Our solution shows an apparent adaptivity to decline the predictions to a very low level and recover afterwards. Furthermore, we plot the query patterns to the memory bank in the bottom. It is obvious that our method can distinguish the Blade-Art Johnson from a regular holiday. The Martin Luther King's weekend, and also from the regular weekday patterns. Generally, in this plot, the lighter the color, the higher the weight time queries in the memory items. Thus, memory item number 2 and item number 6 stand for the nighttime and daytime mobility patterns, and irrespectively, as the case demonstrates the event's awareness as the short-term event causing sudden drift. More surprisingly, the event blade-art drownness has never occurred in the training dataset from the predictive model. And here is another study case, and in which we use the aforementioned memory augmented dynamic filtering network. In this one, we measure human mobility by point of interest visitation. And we choose COVID pandemic as our target events. There are 10 classes of POIs 10 classes of POIs according to the US code, and including the supermarkets, restaurants, and office, etc. Here we use a stream graph to visualize the multi-class results. The stream graph is a special stack graph by optimizing the widget value from the ground truth value of state average POI visits. We can tell there is an overall decreasing tendency from end of April and to the end of May 2020. While the state-of-art model extracted an updated increasing trend, our model can not only capture the big picture's declining pattern, but also special attentions to the details. For example, for smaller scales, POI visitations of the memory days. Yeah, and so let me make it fast. And in the next research study, instead of utilizing the sample-specific parameters to generate graph convolution kernels, we use it to learn the dynamic graph structures. And here we can see that for the traffic accidents, our graph convolution networks can automatically adjust itself to learn the dynamics in the traffic. So so here in our works, and we proposing a promising approach that towards adaptive urban mobility predictions based on anomaly detection and meta-learning techniques. And here is the project list that's related to the previous work we have mentioned. And in the future directions, we want to have stronger backbones for spatial temporal modeling, and also for more efficient parameter inference for the deployed system. Okay, so that's all. Thank you.